So I think for this morning's pre-coffee session, you're going to have to imagine that you've been transported to South Africa because it's me and my colleagues for the morning. And most of us will be talking about our baby, the MeerKAT telescope, which you can see here in a picture in the Karoo. So what I'm going to try to do is give you a little bit of background, and I'm actually going to back up to my presentation in China last year and start with a few of the slides that I ended off with there, and just update some of the science results, the most recent science results. And then I'll try to weave in a couple of stories. So this is a very non-technical talk, trying to pick up from where the teaching left off on Monday with some fairly practical, hand-wavy lessons. And I'll try to weave in as many stories as I can fit. So this was an image I showed last year. This is not a radio image. This is an optical image. This was taken by the MeerKAT telescope. So the MeerKAT is a kind of order of 1 meter telescope that's built in Sutherland. It's a few hundred kilometers away from MeerKAT. But as the name implies, it's tied to MeerKAT. So MeerKAT basically couples to the MeerKAT control systems, and wherever MeerKAT points, MeerKAT points. And it just captures whatever it gets. And if something interesting happens, then we immediately have an optical counterpart to compare. So this is the optical image. And for the people who are new to radio astronomy, why do we do radio astronomy? Well, if you add the radio image to that, these are just the overlays of the two, then you see a very different picture. So there's a lot of information in radio that's very useful, and it complements the knowledge we can gain from all of these. So this is our it's close to first light image, and this is a stunning image of the center of our own galaxy. And a lot of these features were captured in detail not previously known. And this particular observation, not this image, but the observation, the bigger observation, is the subject of some ongoing research, which hopefully will be published very soon. So in addition, this is a kind of a status slide. What's going on? Well, we have these large survey projects. I'll tell you a bit more about what large survey projects are later. So 3 of them are collecting data. That's with a 4K/1K modes. The names are there, and 5 are awaiting further development. So while the telescope is up and running and taking science data, the engineers are still very busy developing bits and pieces that are still coming online. So of those, there is a 32K mode that's pretty close. There's a narrowband mode. There's a UHF band. So the L-band receivers are all deployed. UHF band is almost all deployed, but not quite. And then there's a whole bunch of other user-supplied equipment that's coming. So I won't go into the details there, but the list is there. See me if you want to talk about details. And on the 5th bullet point, there's an S-band receiver that's actually being built by the Max Planck Institute, and they will shortly deploy all of those on our site. And in the meantime, there's a lot of commissioning going on. So there's this competition for telescope time between engineering, commissioning, and science. So we're quite stretched. Having said that, and I'm not an expert in this, so I won't be able to defend this claim, but the claim has been made by people that I trust. This is the most sensitive radio map ever made. And every dot here is a galaxy. So, and there's lots more where this comes from. So as MeerKAT is starting to explore skies that have previously not been explored with this sensitivity, we are coming up with very interesting discoveries. And I won't go into the science, but this is already being used to constrain some models of galaxy evolution. So that solid line over there, that's new MeerKAT data that's adding to the science. This is another very recent publication. So discovering the missing hydrogen in the Fornax A. So most of that missing hydrogen is actually, if I could just point it out, in these clouds along these lines here. And that's solved a long-standing puzzle about why is this galaxy so much less massive than it should be. And just browsing through some imaging results. So MeerKAT's coming up with very at least visually interesting looking things, some of which are not yet explained. And here is just a collection. There are 5 images here. I'm not sure if you can see 1, 2, 3, 4, 5, and then this little piece here is zoomed in over there. Here's another composite image. So in this case, it's MeerKAT and Spitzer data, infrared and radio. I'm not sure, I'm colorblind, but the blue is radio and the red is infrared. And you can see the composite images and the resulting science from that. So in MeerKAT, we had to do, our program had these large survey projects. And when we started commissioning MeerKAT, we had to do science that would not tread on the toes of the large survey projects. And here is some work that we've done with that. So this is a survey of the galactic plane. There's some details over there. So here is an image. It's a mosaic image, and here's some detail. This is one of these observations, and this spans a fairly large part of the sky with resolution such as that. Some comparisons. So this is previously the best image of a certain object, and this is from MOST, and that's the MeerKAT version of it. So you can see the detail is starting to emerge quite nicely there. These 2 images are rotated with respect to each other, so just in your head you have to just slightly twist them. And there's another one. So this blob turns into something that you can start to investigate a bit on the left-hand side. And then there are other discoveries. So on the left-hand side here, there's what appears to be a relativistic, a neutron star moving at relativistic velocities. And this kind of thing is now being investigated. So the data is captured, the images are made, but people are just getting around to analyzing it. This is from our chief scientist, what's going on here. So the projector doesn't quite do this justice, but you can see the sensitivity bringing quality to imaging that's really quite spectacular. And then we've sometimes run out of acronyms. So there are some objects that have previously been detected. So this is a previous survey, but the detail that MeerKAT brings enables opportunities to investigate what is actually going on there. Right, so that's all the latest science, and please do look out in interesting journals for more. There's a lot more coming. But let's step back. So why did we do this in South Africa? And here's a map of South Africa. As we zoom in to the site, you'll start to see that this is kind of an arid region. There are not very many people around there. And so there are very few telephones, computers, radio stations, TV stations. So the radio quietness of the site is really absolutely key to why we've gone there. It's about 800 kilometers from Cape Town, so it's quite painful to get there. Jack will tell you the stories about driving up and flat tires and car problems and everything else. But the gain is that we're very far away from major interfering transmitters. So also on this picture you can see there's KAT 7. So KAT 7 was our engineering array, not intended to do science. It did a little bit of science. That's now switched off and parked, and this is the MeerKAT layout. So every dot is a MeerKAT antenna, and we can zoom in a little further into this image.
What's the scale? So
I'll get to the scale in a minute. So on KAT 7, the longest baselines are about 80 meters, to give you an idea there. On MeerKAT, the longest baselines are 8 kilometers. So the furthest 2 antennas are 8 kilometers apart. And here you can see KAT 7 in the foreground, and you can see the MeerKAT spread out over the entire valley in the background. There is also, we do host, this isn't a Google Earth picture, so it's a little bit outdated. We do host other instruments. So that circle over there is where Hera is being constructed at the moment. Okay, so that I think that line represents 80 meters, and that one is 1 kilometer. So you can see the core is quite dense. 39 antennas are within 1 kilometer diameter. Have I got that right? Yeah, it's about that. And then the outlying stations get a little further spread apart. The other thing to point out on this picture is the little yellow place marker right at the bottom. So that's where what we call the KAPB, the Karoo Array Processor Building, is located. That's where all of the processing happens. So from these antennas, all the signals go back to there, and the correlator is installed there, and the science data processor is installed there. So the choice of that site is also significant. This over here is called Losberg, loosely translated as Loose Mountain. And the Karoo Array Processing Building is basically behind this part of the mountain. So the mountain gives us shielding towards the core. And there's line of sight to only one antenna from there. So that RFI shielding, that's deliberately chosen to give us an extra level of shielding between our own equipment and our antennas. So what does that look like? So this is a very small subset of the band below 180 megahertz. You'd have to just imagine this carries on. But the orange marked spaces here are the unflagged data. And this is a comparison of the MeerKAT site at the top with an American site actually at the bottom. And so you can see that this distance from civilization pays off quite handsomely in available band where you can do science. Okay, so a little bit about the engineering. So picking the site is one thing, then you still have to build the instrument. There's a picture taken out of our scheduled flight that goes up to site. You can see the core in construction. Some more visuals of the antennas on site. This is the process of actually assembling the main reflector. So there's a dish shed over there. That's the same building as on this picture here. And inside the dish shed, you could fit 3 antennas in various stages of production. So the individual panels, it's aluminium panels, are shipped to site, and all of the backing structure components are shipped to site. And then the assembly of that happens in that in this shed. And then the pedestals are also shipped to site, and the pedestals are mounted, so the pedestal is over there. And once the dish reaches assembly stage there with a few panels removed to be able to hoist it up, you get a big crane and mount it onto the pedestal, and then the rest of the assembly installing this secondary reflector. And over there you have the feeds and the digitizers mounted on a turret. There's a picture of a feed. There's some more pictures coming. Here is the Karoo Array Processor Building with Losberg in the background. And the signal processing and compute is all installed in a room over there. This is just the air conditioning duct, so right next to it is where the processing happens. And that room, this building looks kind of flat, and that's because it's partially buried underground. So that's another aspect to the RFI protection, to bury the building underground. Then, in addition to that, the entire compute area is shielded, so it's within a Faraday cage. While they were doing this construction, interesting side note, our RFI manager, Karel van der Merwe, stumbled upon the idea to use the soil that was excavated in burying this building, and he placed it in a berm from which this picture was actually taken. So on this side here, there's a berm. And that berm provides an additional 20 dBs, depending on the frequency of shielding. So RFI, 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 that's kind of what I'm saying. You've got to think of this every step of the way. So the reflector dishes, we call them receptors. The red lines here are basically showing where the beam comes in, bounces off the main reflector onto the secondary reflector and into the feed. So we have feeds mounted. The L-band feeds are all mounted and operational, 900 megahertz to 1.67 gigahertz. Behind the feed, there's a digitizer, and we can actually mount 4 receivers on a turret and rotate them into focus. So you can operate at different frequencies. So today we have L-band. UHF band is almost fully deployed. That's 590 megahertz to just over a gigahertz. So this design is, again, carefully chosen to provide the best sensitivity. So you get very low ground spillover. You get a very nicely circular symmetric beam. And that's important because this is an alt-as mount. So as you're tracking a source across the sky, the source will rotate. So if it's circular symmetric, then it simplifies the calibration as that source rotates. So here are the more pictures of the receivers. Not much detail to say there. I need to speed up a bit. Then I want to say something about the design for RFI. So you start off on the schematic before you even get here. You think about RFI every single step of the way. If you don't need a clock, you don't design it in. It means compromises. Sometimes you have to run things at a slower speed, but you start there. Then the next step is you design the printed circuit boards with everything that you can shielded between layers of ground planes. And you carry on. You put those printed circuit boards into enclosures like this, and here you can see the RFI gasket. So this is one module. This is actually a timing module that goes inside the digitizer, and this RFI gasket shields this section from this section, two different sections, from the power supply section with a filtered connection that goes out.
And you said these are different ground planes in the board?
So you try to shield everything between ground planes, sandwich between ground planes, so multi-layer boards, yeah. Then those modules, so that module is not here. But it would slot into one of these slots. These are now each individually shielded. So on top of the PCB design, the internal shielding, they're individually shielded, and they're interconnected with fiber. So it's short range, but the fiber prevents any coupling from one unit to another. So here we have RF conditioning units, and we have samplers. We don't want those things to couple to each other. And then, even though we've designed all of this, we test it, and we test it to death. So this picture is not very clear. We have a reverb chamber. It's kind of the opposite of an anechoic chamber. So there's a stirrer. This is the motor for the stirrer, and that stirrer rotates. The walls of the chamber is covered with a deliberately reflective material. And so you can excite all the different modes in this chamber in a very short time. So you don't know where signals are coming out, but you know if they're coming out. Every single thing we build goes in there, probably from PCB stage, so before you shield it, so you know how much shielding you need. Then once you've shielded it, and again, once you've integrated. So RFI, RFI, RFI everywhere. And the results of all of that is what I'm trying to show here. So this is a comparison of the VLA single dish with a MeerKAT single dish. So despite the size difference, the performance of the sensitivity of the MeerKAT single dish. So the red is predicted, and this turquoise is predicted, H and V, and the blue and green are the actual measured results. And so if you look at that sensitivity over there on this graph compared to the VLA over there, you're getting, with a 13.5 meter dish, pretty close to the same performance single dish. So I mentioned the large survey projects. I'll leave this as an exercise to the listeners to go and look at. The information's there if you're interested. There's a list of large survey projects. Here they are. They're kind of color-coded, so the blues all go together. There's some data rates. Again, I don't want to go into the detail, but if you want to look it up, you can have a look at that. This is the science data processor that follows that. So there's some interesting stuff here with Ceph archives. And so you put that all together and you get that. It's just a lovely picture that Amish shared with me yesterday. And this is basically all the antennas pointing in the same direction. So we were very happy when we saw that the first time. Here's another picture of the Karoo site. So there you can see the berm, which is providing us additional shielding. And then, after all of that, this is what happens. So I've been hammering on about RFI, RFI, RFI. Here's the result. So this is an RFI monitor on site, 2 plots, and you can see this area. This is the difference. I'd like to offer anyone a guess. What's the difference between this plot and this plot? Wi-Fi? But why is there Wi-Fi here and not there? Look at the dates. 2 days apart. No, fortunately not. This is a Sunday. The top plot is a Sunday. and the next dot is a Monday. So RFI, even though this is our own people causing this, it is almost impossible because you are up against human nature. So this is cars, phones, Bluetooth left on, and that's actually the end result you get. So it's an endless battle, and you really, really, really have to fight that battle very hard. Thank you.